Welcome to ilectureonline. In this video we're going to talk about the delta to y conversion. It's a very famous conversion, something that's really unique and very beneficial, especially when we start trying to solve things such as bridge circuits or bridge networks. Anytime you have a triangular shaped network like this, it's very difficult to figure out which way the currents will go because the currents can split up in different directions depending upon what A, B, and C are connected to. Turns out we can easily translate or transform a delta connection like this into a Y-shaped connection. That's why they call it a delta to Y conversion. This looks like a delta. In this case, it's an upside down delta, and this looks like a Y. Now, this will be electrically equivalent to this circuit. The question is, how do we make that conversion? And the easiest way to do that is to draw the delta right in, I should say the Y connections right inside the delta connections. So if we draw this in here like that, there's my R sub A, there's my R sub B, and there's my R sub C. So this is R sub A, R sub B, and R sub C. Notice we have the very same connections. This Y connection will be connected to the very same nodes as the original circuit. But now we need to make a translation between R1, R2, and R3 to RA, RB, and RC. Notice that RA is situated between R1 and R2, RB is situated between R1 and R3, and RC is situated between R2 and R3. It is key to see that. Once you see that, then it's easy to understand how the equations are done. RA is equal to the product of the two resistors it's in between. So in this case, it's the product of R1 and R2, and is divided by the sum of the three resistors in the delta, R1 plus R2 plus R3. It turns out all three of them will be divided by the sum of the three resistors. RB can now be found to be equal to the product of the two resistors it's in between. RB is between R1 and R3, so this becomes R1 times R3 divided by R1 plus R2 plus R3. And finally, to find RC, again, notice that RC is between R2 and R3, so this becomes the product of R2 and R3 divided by the sum of R1 plus R2 plus R3. The reason why this is so powerful is look at the following example. Let's say that we have a bridge circuit that looks like this. We have a resistor like this, we have a resistor this way, we have a resistor going in this direction, then we have one more in this direction and one more like this. Notice we can take perhaps the bottom part of the circuit and realize it looks just like what we have over here. This can be considered R1, this can be considered R2, this can be considered R3, which means we can pull this out of that circuit and replace it by that one, which means we now have a circuit that looks like this. Like that. And now that one will be replaced by the following. And electrically, this has the very same effect. If we call this, let's say, R4 and R5, just to give it a name, and so this is still R4 and R5, notice that the bottom portion of it, that delta, now gets converted to a Y, and this resistor here will now be R sub A, this resistor here will now be R sub B, and this resistor here will be R sub C. And that one is easy to solve. We can very easily find the equivalent resistance of this, because notice that now these two are in series. Those two resistors are in series. We can combine those two. Then those are in parallel, and that parallel connection is in series with R sub C. So we can very easily find the equivalent resistance of this, which then allows us to very easily find the current flowing to the entire circuit using that Y to delta conversion equivalence. And that's what this is all about. So again, find your delta, draw within it the Y, label the Y resistors, and then notice that this resistor is between those two, this resistor is between those two, and this resistor is between those two, and that's how we derive the three equations to convert from one to the other. On the next video, we'll do an example of this. We will numerically work one out so you can see how to find the values for RA, RB, and RC.